clearly, again, it's space plus time that's the correct arena. It's world lines that we have to deal with. That's the quantity that's related to geometry. We don't know what the geometry of this space plus time is. We're going to try to find it. We try to define it according to straightness, according to inertia. We found there's no such thing as inertia. The straightest line in space plus time looks curved to us, looks accelerated, no surprise. So we draw it this way. How can we really draw it? Well, that's a problem. There's something strange about space plus time because the straightest possible line of space plus time turns out to be curved. So clearly space plus time does not have maybe the naive properties that maybe we would have thought. Now we know what the properties of space are because we live in it. We know what the properties of time are, somewhat, right? We're familiar with it. We don't a priori have a notion of what the geometry of space plus time ought to be like, right? I mean, space plus time is not something that we directly have experience with. So we can't just arbitrarily ascribe to space plus time properties, geometrical properties, without investigating. And when we investigate, we find that in fact the properties are a little bit strange. That the straightest line is what to us looks like a curved line. So we have something of a conundrum here. We have the straightest possible world line has a curvature, right? Remember this curvature, the second derivative, gm over r squared. How can it be that the geodesic, and all the properties of a geodesic, given the beginning, the initial tangent, you can reconstruct uniquely the whole extent of it, right? It's as straight as possibly be at every point. It has all the properties of a geodesic. Just it's curved. All right, so the problem is that we're going about it in a mixed, naive way. We're saying we have the space plus time. We don't know what the geometry of this space plus time is. We're going to try to find it. We try to define it according to straightness, according to inertia. We found there's no such thing as inertia. So we have a more sophisticated space plus time. So we can't draw axes like an x and t axis in our flat, ordinary, unsophisticated piece of paper and expect that the diagram that we're going to get is actually representative of what's really happening in space plus time. We would need to be in some free fall frame on some kind of a. When you draw a gravitational world line, you just draw it as a curved, right? It's accelerated, so it's a curved line. But you're drawing that again in this non-sophisticated space plus time connected out. You would have to kind of twist the axes in some way to represent this sophistication of the space plus time, and then draw this line. If you did that, you would find that the free fall world line was in fact the straightest possible line. Okay. At this point, we're ready to jump into general relativity. Up to this point, we were kind of neo-Newtonian. I didn't really introduce anything that's not Newtonian. No special relativity. There wasn't anything that Newton, in theory, couldn't have followed immediately. Right? He even knew about free fall. He computed some very nice riddles, and he used these properties of the equivalence principle in computing things. There's nothing really non-Newtonian, but it's kind of neo-Newtonian. Especially talking about space plus time and the idea of defining these straight lines, defining straightness, and so on. Now, to jump into general relativity, what we would say is, okay, we have this interesting property where the straightest possible lines seem to be curved. We understand that we took too naive a view of what space plus time is. So let's say that space plus time is warped relative to our usual conception, and the straightest possible lines, when represented in this wrong frame, turn out to be curved. But if you would draw them correctly, they would be straight. In other words, space plus time is curved. The free fall world line is straight. If you want, you can think of our graph with space plus time and the curved world line for gravitational free fall. And by warping the axes in the right way, you're straightening out this line. So you get a straight line in a warped space-time. If you look at that diagram the wrong way, like this, you get a curved line. Okay? And that's basically Einstein's theory. Space-time, in his theory, space-time, this is naive, space+time. Space-time is warped. The type of warping that it has is the type that we can call curvature. We're going to see more explicitly and more precisely later on why curvature. But at this level, why would I say that it's the type of warping that we can call curvature? Because it uncurves this line to make it straight. So in this kind of warped space-time, what was curved is now straight, and what's straight becomes curved. Okay, so because of that, we'll call the nature of the warping of space, and we'll call it curvature. And again, we'll see that better later. So we have a warped or curved space-time. Particles have inertia. What does it mean, particles have inertia? It means that there's an inertial field on space+time. What is this inertial field? We know it's a world line curvature, connection curvature field equal to gm over r squared. Right? And that is the straightest possible geodesic line in space-time. So just like a particle moves with a constant speed in a constant direction and you accept that, well, that's inertia, particles accelerate. When you look at it in the wrong frame, you're looking at the source frame, they seem to accelerate. Yes, why? Because really what they're doing is inertial motion, gravity inertia motion. Their world line is geodesic of that curved space-time. So again, for all intents and purposes, as far as we're concerned, when you're in free fall, you're in an inertial state. When you're not in free fall and you're fighting gravity, you are in a non-inertial state. Therefore, the straightest world lines are world lines of free fall particles. And again, that tells us something weird about space+time, because we know that the geometry of space+time is such that the straightest possible lines in it are what to us look like curved lines. Another way of interpreting this, and with this we kind of jump into general relativity, is to say, instead of having curved world lines in this diagram and somehow saying that's the straightest line, which is kind of absurd, we have to recognize that space+time has weird properties. It's warped, and we would have to draw the axis in some strange warped way to represent reality. And when we did that, we would kind of stretch out this line. Instead of being curved, it would suddenly become a straight line, or the straightest possible line. It's only because we're drawing the axes like this, which is illegitimate for representing this warped space-time, that we get a curved line. So because we're uncurving this curve by warping our axi, we can consider the warping to be curvature. We're giving curvature to space+time, and in the appropriate axi for a curved space+time, that what otherwise would have been a curved line becomes straight, or straightest. Where can you see an analogy of this? I showed slides last time of the globe, the Earth, right? If you fly from Europe to New York, you might fly over Newfoundland, Labrador, right? If you look on a map, it's flying like this, on a flat map. Why is that? It's actually not, if you look on a globe and you draw the line, you'll see it's a great circle. Maybe you've learned that a great circle is the shortest distance between 2 points on a sphere. All right? If you took a sphere, if you took the map of the Earth on a sphere and you cut it off, you pulled it, you peeled it like an orange peel off the sphere, and then you tried to flatten it, you can't. You have to cut it like a petal of a flower in order to get the shape to be flat. And then you have all kinds of strange things like, you know, countries split in half, and one part of the country is here, another part of the country is on the other petal near it, and the other, and so on. You have a distortion. When you look at a regular map, which is continuous, the distances and the geometrical relationships are distorted. They're not accurate, because they've arbitrarily kind of, well, not arbitrarily, but they flattened out what actually is a spherical surface. So the true geometry can only be determined when you look at the globe. So what looks like a straight line on the map is actually a non-straight line when you look on the globe, and what looks like a curved line on the flat map, like going up to Labrador and then going to London, is actually the straightest possible line on the sphere. Now, it's the straightest line on a sphere. It's not the straightest line on a flat piece of paper. Okay? On this flat piece of paper, which is a map, the straightest line is the straightest line. But it's only a representation of the reality, which is a globe. So it's not really the straightest line. It's the straightest line only if that flat map represented the true reality. So we're used to drawing axes in flat space on a flat piece of paper, and we're expecting that the straightest line will look like this. But it's just not so. We're representing a space plus time which has warping of the type that's called curvature. And therefore, the straightest possible line will in fact look like this, right? A free fall world line. This world line curvature, which in the more sophisticated version we'll say is some kind of curvature of the space-time.